This is going to be lesson 63-2. We're going to take a look at the real zeros of polynomials and complex zeros. Today we're going to be finding the zeros of a polynomial, and this includes all zeros, which includes the imaginary. Now remember, we call those complex zeros. It's both the real and imaginary zeros all combined together. So the first theorem, fundamental theorem of algebra, it says suppose if f is a polynomial function with complex number coefficients of degree n being greater than or equal to 1, then f has at least one complex zero. Now this theorem is basically just an existence theorem in mathematics. It guarantees the existence of at least one zero, but we still don't necessarily have an algorithm to actually be able to find it. And so based upon the fundamental theorem of algebra, it just basically says, hey, you can find a zero, or at least their zero does exist. And so we have to use our tools to be able to find what those zeros are. So one of the first theorems is going to be the complex factorization theorem. And this says that suppose f is a polynomial function with complex number zero coefficients. If the degree of f is n and greater than or equal to 1, then f has exactly n complex zeros counting multiplicity. Now what's important about that is it's saying that the degree of the polynomial, okay, the degree of the polynomial is the number of zeros the polynomial has. If z sub 1, z sub 2, all the way to z sub k are the distinct zeros of f, then we're able to write it in terms of whatever my leading coefficient is, x minus your 0 with some multiplicity power times x minus my next 0 with some multiplicity power all the way down to x minus my k0 multiplicity based upon that k0. And so I can break them all down into its purest factor form. All right, so first example. It says find all the complex zeros of our function and state their multiplicities. So to be able to find the complex zeros of this polynomial, we have to try and factor it. Well, to be able to factor it, or at least find the zeros, there's nothing in common. It's not a trinomial. There's no difference of squares. So remember that we said that another form of factoring is polynomial division. Now to find the numbers that I need to divide by, we're going to use the rational roots theorem or the rational zeros theorem, which is my p's over q's. And so my p's over q's are going to be plus or minus 1. It's the factors of this number divided by the factors of this number. So we have to do that. So listing all those, I get plus or minus 1/2, plus or minus 1, plus or minus a third, plus or minus 1/4, plus or minus 1/6, and plus or minus 1/12. So I need to try all those. So what if I try positive 1? And you go through and you're going to have to spend all this time, setting it up to divide. And so bring down the 12, multiply, add, multiply, add, multiply, add, multiply. Okay, it's not going to work. Let's try positive 1/2. So remember, we have to go through and write out all the coefficients. So bring down the 12, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. So that works. Now, what if there's multiplicity? Right? So I know that this is a 0. This is a factor of x minus 1/2. But I don't know if there's any multiplicity. There might be. And so I have to check 1/2 again. And so checking 1/2 again, bring down the 12, multiply, add, multiply, add, multiply, add, multiply, add. So it works as well. So I also have another. So now it's x minus 1/2 squared because I have 2 of them. And so now I have to continue and check more. Now as we keep checking, negative 1 won't work. Maybe I'll try 1/3. Let's see if 1/3 works. Bring down the 12, multiply. It's going to be 4. I get negative 4. Okay, that's not going to work. What if I try negative 1/3? Bring out a 12, multiply. Gives me negative 4, which is negative 12, multiply. That's going to give me positive 4, so that's 12 multiply. So that works. And so now I'm going to be left with 12x squared minus 12x plus 12. Now there's a 12 in common there, so I can factor out a 12. And now I'm going to have to use the quadratic formula to be able to find what my remaining zeros are. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So I'm going to get 1 plus or minus root 3i all over 2. Now that can be broken up into 1/2 plus root 3 over 2i and 1/2 minus root 3 over 2i. So all of my zeros, if I'm going to list them, right, we said we have 1/2, which is multiplicity 2. We have negative 1/3, which is multiplicity 1. I have my positive 1/2, root 3 over 2i, and then I have my 1/2 minus root 3 over 2i. I have 1, 2, 3, 4, 5 zeros here, which matches what my complex zeros theorem is going to be. So when I want to factor this, remember we said that we have 1/2 multiplicity 2, negative 1/3 multiplicity 1. We had 1/2 plus root 3 over 2i, and we had 1/2 minus root 3 over 2i. Now for us to write this as a factor, if you remember in that other slide, we had this a that we factored out. We can't forget that. So my a is going to be 12. And so writing it out, it's going to be f of x equals a times x minus your 0 multiplicity 2 times x minus my 0 times x minus my 0 times x minus my 0. And so that is going to be the full factored form of this polynomial. Now we're going to take a look at the non-real and irrational zeros theorem. What this theorem states is if a complex number a plus bi doesn't equal 0 and it's a 0 of my polynomial function with real coefficients, then its conjugate a minus bi is also a 0. So for example, if I know that 3 minus 5i is a 0 of my function, you have to assume that the conjugate 3 plus 5i is also a 0. And this also works for irrational zeros as well. Now the importance of this is it's a way for us to assume information based upon certain circumstances. So now readdressing Descartes' rule of signs here, the first thing is that the fundamental theorem of algebra and that complex zeros theorem, remember it said that we know that zeros exist and that there are an n degree number of zeros. Then that complex zeros theorem says that all complex zeros, when in terms of imaginary numbers, exist with conjugate pairs. And so we're going to use these two theorems together to kind of readdress what our Descartes rule of signs is. So this was a problem in our previous slides that we've used before, and I already solved it out. Remember, we count the number of variations of signs, and so I said the possibility was 4, 2, and 0, and for my negative zeros, we said that it was just 0. Well, I can create a chart. My n is the total number of zeros that I could have, which in this case it's going to be 4. Now the scenario of my possible positive zeros is going to be 4, 2, and 0. And I can only have 0 negative zeros. Now if I add these across the board, they need to add to 4. Well, 4 plus 0, well this has to be 0 for it to be 4. 2 plus 0, well this has to be 2 for it to be 4, and this has to be 4. Now notice that the way that my imaginary zeros exist, they exist in those conjugate pairs that I just mentioned. And that's essential. That is the reason why it counted down by an even integer, is because of those non-real zeros. Okay, they always exist in conjugate pairs. So on this next one here, if you remember, we count the variations and we made our conclusion based upon the variations. And so we can go through and fill this out. So the number of possible positive zeros I have is 2 and 0, and the number of negative zeros that I have is 1. Now my n is 5, and I get that from right here, so my n is 5. And so they have to total up to 5, and so that's why that's going to be 2, and that's going to be 4, so each row adds up to 5. And so once again, everything, these are even values, these are even integers, they are expressing themselves in those conjugate pairs. Now the last thing, and this theorem is just being mentioned, we're really not going to practice too much with this, but the real factorization theorem just says that if you have that polynomial function, when you factor things, you could leave them in either linear factors and irreducible quadratic factors. So if you remember that one where I had that quadratic equation x squared minus 1 plus x, minus 1x plus 1, when it was like that. Well, and I said that if I use the quadratic formula, I can say that that's x minus 1/2 plus root 3 over 2i, and then x minus 1/2 minus root 3 over 2i. So we said that we can write it in terms of that x minus your 0. Well, what this theorem is saying is like, well, you don't have to leave it in terms of the complex. You can just leave it in terms of this irreducible quadratic. And that's also another way of factoring. We're going to mainly focus on this way. I'm just mentioning it because sometimes we're allowed to leave it this way, but I want to focus on being able to write them out in terms of reduced complex factorizations. So on this one here, it says use synthetic division to show that x equals 2 plus 2i is a 0 of f. So to do that, we're going to go through and we're going to do 2 plus 2i. And I have 1 for x to the 4th. I don't have an x to the 3rd. I don't have an x squared. I don't have an x. And then I have my 64. So bring down the 1. Now I'm going to change the color so we can see it off to the side. But now I need to multiply. So it's going to be 1 times 2 plus 2i. So that's just going to be 2 plus 2i. Now add straight down. Now I need to multiply this, so 2 plus 2i times 2 plus 2i. Now if I FOIL that, you get 4 plus, and this would be 2i, and so 4i and 4i, so plus 8i. And then here, 2i squared, that's going to give me minus 4. Because 2 times 2 is 4, I times I is I squared is negative 1, so that gives you minus 4. So those are going to cancel out, and so you're going to get 8i. Add straight down. Now multiply. So 8i times 2 plus 2i. That's going to give me 16i and plus or minus 16, because 8 times 2 is 16i, and I is I squared, so I squared is negative 1. Add straight down, so negative 16 plus 16i. I'm going to write it in a plus bi form. Now multiply, so 2 plus 2i times negative 16 plus 16i. So foiling that, you get negative 32. And then that gives you negative 32i. That one gives you positive 32i. And then the last gives you plus 32i squared, but that's going to become negative 32. So negative 32 and negative 32 give you negative 64, and so therefore it is a 0 of it. So step 1, check. Now step 2, it says find the remaining complex zeros of f. So here's a good one. Now the reason why it's a good one is because the complex conjugate roots theorem states that also the conjugate exists. And so a 2 minus 2i also exists here. And so I'm going to take my coefficients of my remaining polynomial. Well, it's not really even a polynomial right now, but my remaining value, so 2 plus 2i, 8i, and then negative 16 plus 16i. Now you're going to watch this simplify really nice. So multiply these together, you get 2 minus 2i, add straight down, you get 4. So multiply those together, you're going to get 8 minus 8i. Add straight down, you get 8. Multiply those together, you're going to get 16 minus 16i. Those add together, you get 0. And so you're left with x squared plus 4x plus 8. So that's one of those zeros. And then now I have to use the quadratic formula here, so negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So negative 4 plus or minus, this is 16 minus 32, so that's negative 16. So negative 4 plus or minus 4i, so I get negative 2 plus or minus 2i. So those are my other zeros. So this does conclude our lesson. If you guys have any other questions, please leave them in the comments.